And we'll close with some talking about different types of evaluation metrics, about how you evaluate your model. First, a couple of announcements. As I hope all of you know, homework 1 is due tomorrow. It's due via Moodle, 9 p.m. tomorrow. It will be graded within about a week. Homework 2 will be released either tonight or sometime tomorrow, or early tomorrow. It will be due the following Friday, again 9 p.m. on Moodle. And there's a recitation tonight in Annenberg 105 on linear algebra and related concepts pertaining things like vector calculus and stuff like that for those of you who may want to brush up on those topics. Okay, so just a quick recap, just so we're all on the same page again. We have training data in the form of xy pairs, where x is a feature vector. In this case, it lives in a d-dimensional space. And y, in the case of classification, or binary classification, is a discrete label that takes on values either +1 or -1. We choose a model class. Here we're working with linear models, which opposes a linear scoring function over the parameters of the model, in this case, a vector w and a scalar b. We have a loss function that characterizes the mismatch between the prediction and the ground truth. In this case, we were looking at squared loss, which characterizes the mismatch penalty using the squared distance. And we put all those together into a learning objective that sums over the loss of the predictions for every example in our training set, and then we simply want to find the W and B of our linear model class that minimizes this loss. And this leads to an optimization problem, and solving this optimization problem is our learning algorithm, right? So this is just a basic recipe for supervised learning. We talked about bias variance trade-off, right, where, depending on the size of your training set, you may want to use a more expressive or less expressive model class because there may be variability in the model class that you can't control for unless you have a large enough training set. And here, as an example, as you may recall, we looked at a comparison in one-dimensional regression between a linear, a quadratic, and a cubic model class. And for training sets of size 7, the quadratic model class ended up best optimizing the bias variance trade-off, where the bias is simply you look at the mean prediction. So if you repeatedly train a model class over training sets of size 7 in this case, right, the bias is simply the deviation of the average prediction of your model, trained model, versus the ground truth on the test distribution. And the variance is, you look at the variability of any individual model's prediction versus the mean, right? And the test error can be written as the sum of the bias plus the variance over the over the test distribution. So even though the cubic model class has lower bias, right, on average it can fit the data very, very well. It has high variance for training sets of size 7. And so in this particular case, the quadratic model class best optimizes the bias variance trade-off. And so the complete pipeline is your training data, you choose a model class or multiple model classes, which we'll talk more about in the next lecture. We have a loss function. We set up a training problem. We train using stochastic gradient descent. We talked about in detail in the previous lecture. We do things like cross-validation in order to achieve two things. One is to measure give a measurement of the error on the test distribution. That's what validation allows us to do. And it also allows us to do something called model selection, which I'll talk about in the next lecture when we're dealing with multiple model classes. So that's a recap of the first 3 lectures, first 2 lectures. Today, we'll look at beyond basic linear models, and so that means feed-forward neural networks. We'll talk a little bit about that. We'll also talk about different ways of training linear models under more sophisticated loss functions, such as those that give rise to support vector machines and logistic regression. We'll talk about different ways of interpreting these models. It turns out that there are multiple equivalent ways, mathematically equivalent ways of interpreting these models, which means you can derive them from multiple perspectives. And that is something that's quite nice about some of these models, which suggests that they're very fundamental in some sense. And then we'll close with a discussion of different types of evaluation metrics. So first, the first part. So just a recap, right? So for the most part, we've been talking about squared loss as the loss function to optimize during learning, right? So when we actually solve this optimization problem using stochastic gradient descent, as you'll do in the homework, right? maybe some of you have already done it, you're optimizing over square loss. It's an easy to differentiate loss function, therefore it's easy to derive the gradients, and relatively easy to optimize, right? When we're doing classification, however, right, the labels are either +1 or -1, right? And the prediction is typically the sign of the raw score, right? So if the true label is +1, right? And if the x-axis denotes the score of our model, right, f of x, then as long as the score is above 0, then we get the classification correct. And as long as the score is below 0, we get the classification wrong, right? So in some sense, 0-1 loss is the loss that we care about, in some sense. But of course, 0-1 loss is intractable, right? It's flat or discontinuous everywhere, right? If you look at this function, as we talked about before, if you're right here and you're doing, let's say, gradient descent, you look at the slope of this line and it's flat. You don't know if you go this way or this way, whether or not it's going to improve the loss function. Whereas squared loss, it always gives you a slope that tends towards the point, the prediction that gives you the lowest loss. So if you're right here, right, you don't know that if you go a little bit in this direction, you'll suddenly achieve 0 loss. And if you're right here, you don't know that if you go a little bit in this direction, you'll suddenly make a mistake on this example. Right? So it's a very hard function to optimize using methods like stochastic gradient descent. Right. And so typically, we optimize for some sort of surrogate loss function during training, one that hopefully has some behavior that's correlated or associated with the desired behavior, which is minimizing 0-1 loss. In the previous lectures, we simply used squared loss as a surrogate for 0-1 loss, and indeed, if you can perfectly optimize squared loss, achieve a squared loss of 0, by implication, right, you also get perfect 0-1 loss, right? Of course, if you don't achieve perfect squared loss, which is generally the case in practice, you can't really say anything because the behavior is quite different otherwise, right? So today we'll talk about a few different loss functions. We'll get at hinge loss eventually, which is the loss function that's used to derive SVM training. So support vector machines, also known as SVMs for short, they're also known as max margin classifiers. So if I take a look at these very simple two-dimensional data set, right? We have positive examples and negative examples in the form of black circles and white circles. And suppose we have 3 hyperplanes that separates the data, right? If I were just to evaluate over these 3 hyperplanes, raise your hands. Who thinks H1 is the best one? Who thinks H2 is the best one? Who thinks H3 is the best one? Okay, good. And it's the best one because it actually separates out the data, right? And furthermore, it separates the data by a very large margin, right? Keep in mind that we drew this data set, we assumed that we collected this data set from the test distribution. So, it could be that if we sampled the data again, there may have been a data, we might get a data point, let's say here, right? Or here, and or a data point of this label, here. And if that were the case, this classifier will still classify those data points correctly, right? And we'll formalize that intuition a little bit later on in this lecture. So just to recall, a concept that's going to be very useful for the first 20, 30 minutes of lecture is the hyperplane distance, right? So a hyperplane is a generalized notion of a line or a plane, right? A line is simply a one-dimensional function. A plane is 2D, hyperplane is many dimensions. And so we can define things like distance from a point to a plane. If we think of W as the tangent normal to the hyperplane, and B as the offset from the origin, right? Then the distance can be written as follows. Typically, people in some communities, people assume that the tangent normal is a unit vector, so you don't need to divide by the normal W, right? Because it's 1, 8, and then B is exactly the offset from the origin, right? And then we often, in machine learning, we talk about sign distance. Are you on the positive side or the negative side of the hyperplane? And how far are you from the hyperplane, right? And our linear model is simply the unnormalized sign distance. This is a recap of what we talked about before, right? And another concept is the margin, right? So for any hyperplane, the margin, for any hyperplane, excuse me, that typically we talk about hyperplanes that separate the data, right? The margin is simply the distance of the closest point to the hyperplane, right? And the achievable margin of a data set is the maximum possible margin you can achieve. So this is the closest point to the data set. This is the closest point to the hyperplane. We maximize over all possible hyperplanes. This is the achievable margin of this training set or this data set, right? And in some sense, the margin is a measure of how stable of a classifier that we've learned, right? And this will become a little bit more concrete in a few slides, right? But suppose we like the idea of finding a hyperplane that has the best possible margin. We want to find this hyperplane that achieves the maximum achievable margin on this training set. We want to find that W, right? How do we do that? So we're going to talk about how we do that exactly, right? So, we could write down the mathematical formula, right? We just take the definition from before and we simply just write it down, right? So we want to find the W of B that maximizes the minimum sign distance from any training point to that hyperplane, right? So if we can solve this optimization problem, we found the W and B, we found the hyperplane or the linear model that maximizes the margin on this training set, right? But this quantity here is in fact the margin of any particular hyperplane. Any questions on that? Yes?
Maybe this will come later, but will this work if the data set isn't linearly separable?
So if the data set, great question. So if the data set is not linearly separable, this will still work with some modifications. Okay. We'll introduce what's called a slack variable, which is very commonly used in optimization. And we'll give some interpretations of that. It's a great question. For now, let's assume the data is actually linearly separable, and we'll talk about the non-separable case towards the end, and that'll lead us to the SVM. Any other questions? Okay, so this is just, again, the optimization problem that we had before, right? One thing that's tricky about this optimization problem is that W appears, which is a parameter in the optimization problem, one of the parameters we want to optimize, appears in both the numerator and the denominator. So it's actually, in some sense, an ill-posed problem, right? I can scale up W by, for the sake of the argument, let's assume that this holds even with B is not 0. So assume that B is 0 for now, right? Then if I scale W up by a factor of 10, it doesn't actually change the answer, right? And this argument holds if B is non-zero as well. It's just slightly more complicated. So which means that there are multiple identical solutions to this optimization problem, which makes this optimization problem ill-posed in some sense. So we would like to constrain this optimization problem so that this infinite number of identical solutions collapses down to collapses, so we don't have to deal with that problem. So there are essentially two ways of doing this. One is to excuse me, that is a typo. That is hold the denominator. Sorry, that's a typo. Sorry. Denominator. I'll fix this on the slides on the, I'll fix this on the slides that I published. Right. So this one holds the denominator fixed, right? We're going to enforce that the normal W is 1. So now we don't deal with this notion of an infinite number of solutions if you just scale W up and down, right? So we're going to hold the denominator fixed. If you hold the denominator fixed, you just pick an arbitrary number, let's say 1, because it's very natural. It's often used in in geometry, because if you interpret the W as the tangent normal of a hyperplane, you often want that to have unit norm anyways for various semantic purposes, right? And so then we can just rewrite the optimization problem as follows, right? And now we don't have this ratio inside that minimization where W appears in both numerator and denominator. And in fact, you can check that this gives us equivalent solutions, right? The solution to the right-hand side is one of the solutions to the left-hand side, right? This is still quite challenging to optimize. And the derivation to support vector machines will take an alternative approach, which is to hold the numerator fixed, right? So we're just going to force the numerator to be some number. Okay? Let's say 1. If we do that, then this optimization problem, right? If you hold the numerator fixed, this optimization problem reduces to an argmax of 1 over the norm of W, right? Or, or you can do, and we'll talk about why we do this, 1 over the norm of W squared, which means we can minimize, instead of maximizing the 1 over W, norm of W, we can just minimize W, or also minimize W squared, subject to this constraint. And I'll write down the full optimization problem in the next slide. Right, and here it is. So this is what's called a hard margin support vector machine. This is probably the most involved slide in this lecture, so I'll go through it slowly. So just as a recap, since I think I want to just say it again, just so we can all digest this information. This was the original learning objective. We wanted to find a hyperplane that achieved the maximum achievable margin on this training set, which is defined by this quantity here. This is the normalized signed distance of any point to the hyperplane. We want to find the minimum at such a point, which is the margin of this hyperplane, and we want to find the hyperplane that achieves the maximum achievable margin. Right? This is the original training problem. Because of the fact that there are an infinite number of solutions in this particular formulation, infinite number of equivalent solutions in this particular formulation of the optimization problem, we're going to constrain it. And there's 2 different ways of constraining it. We're going to constrain it by forcing the numerator to be a constant, in which case we're simply maximizing 1 over the norm of W, subject to some constraints, right? And that's equivalent to minimizing the norm of W, which is equivalent to minimizing the square norm of W, since the square is a monotonic function, right? And so if we believe that, if we believe that this is the right function to optimize, right, minimizing the norm of W subject to this constraint, right, then that leads us to this minimization problem, right? And here I simply added a 1/2 for mathematical convenience in terms of deriving derivatives and other things that people tend to do when they write out the SVM formulation. And so, it's minimize the norm of W subject to the constraint that for all training examples I, the unnormalized sign distance is at least 1, right? So this is a quadratic minimization problem subject to linear constraints. Okay, so a few comments about this optimization problem. So the the minimum possible distance of any data point to the hyperplane is 1 over the norm of W, because the distance of a point to a hyperplane is this divided by the norm of W. Right? And since we're enforcing that to be at least this thing to be at least 1, that means that the closest possible point to the hyperplane, that the distance is 1 over the norm of W, which means the gap between the the actual gap between between this margin that's in the hyperplane from the, let's say, positive example, and this margin, which separates the hyperplane from the negative examples, let's say, is equal to 2 over the normal W, right? And this is the point that actually achieves the equality here. So notice that this is an inequality. So these points, if you compute the score, like y times w transpose x minus v of these points, they're actually greater than 1. And these are greater than 1 as well, right? So here y is here the labels are negative. So if you remove y from this inequality, these are all large negative numbers that are less than -1. And these 3 points are the ones that actually achieve this margin, right? And the margin is 1 over the normal W. Yes, question?
So it seems that if the data set is not linearly separable, that this formulation would be
Correct. We will talk about what happens if the data set is not linearly separable in a few slides. But I really want to hammer home the case where it is linearly separable. Don't try to run before you can walk. So yes, I will talk about that. I will get to that. I just want to really hammer home this point first. So we're going to talk about the case where it's not linearly separable in a few slides. Let's see. Any other questions on this before? Yes?
Do we actually require the existence of I to achieve the lower bound? Or just object and
Oh, okay. So if you actually think about this optimization problem, there will always be an I that achieves this lower bound. And here's how you can see that. If let's say these 3 data points didn't exist, right? If these 3 data points didn't exist, then this minimization problem, which wants to minimize the normal W, will be allowed to make W even smaller, right? It would be, if these 3 data points that sit on the margins did not exist, then this minimization problem that wants to minimize the square root over W would allow it to make W even smaller, and until it hits, let's say, this point, right? And so then the margin is 2 over the normal W, where W is even smaller, which means the margin is even bigger, right? If the margin is 1 over the normal W, if these 3 points didn't exist, the margin is bigger. The achievable margin is bigger, and we'll find that by finding a smaller W. So if you actually analyze this optimization problem, there will always exist an I that achieves equality on this constraint. It may be the case, and furthermore, that there will always be an I on both one on the positive side and one on the negative side, right? Because I can shift the bias term, the offset term, right? So that I can shift this up a little bit so that this guy sits on the margin and this guy sits on the margin, right? So there will always be at least one on both positive and negative classes that sit on the margin. Does that answer your question? Okay, so now we're going to do a quick mental exercise about stability. And I won't go into the formality of it, but if you're interested in the details, they're available on this link right here. So, what would happen if I got rid of this training example? What would happen? Any guesses? What's that? Nothing. Okay, great. What would happen if I got rid of this example? Nothing. Right. In fact, if I do not modify this example, or this example, if I remove any of the other examples, I would get the exact same solution. Right? So what that means is that, so you can do the following exercise, right? If I were to do, let's say, leave one out validation leave one out cross validation on this problem where I remove one data point at a time. So you guys learned about five-fold cross validation. If there are n data points, leave one out. Cross validation is n-fold validation where you leave out one data point at a time. Then if I train this model on leave one out, I would get the exact same model on all but the cases where one of those 3 points was in the test set, was in the validation set too, right? And that is a measure of the stability of this model, right? And these 3 points, by the way, are called the support vectors. They're the support vectors that determine the solution to this optimization problem. Yes?
So could you look at the inverse direction and say that it's not stable in the sense that we got another data point that was just over that margin of high risk solution?
I'm sorry, I don't
I
understand.
mean, by adding data, if you added one of those white point or another white point that was inside of where you currently have that line, it would have a shift in the plane. So is it not stable to new data, but stable to take old data away?
So if you added more data, so the argument that I just made, well, okay, let me see if I can unpack your question. I'm not sure I understand the implications of it. So in the argument I just made, I'm pretending that the training set is the whole set I care about, and I'm going to leave one out of cross validation, and to get a measure of the test performance, and the stability of that measurement is dictated by, in this case, whether or not I make an error, right? Whether or not I because this problem is linearly separable, whether or not I achieve 100% accuracy or not is upper bounded by the number of support vectors, right? And that's the proof is in that paper, but that's a sort of informal analysis. What you're saying is, okay, let's suppose we didn't have all the training data, we were just adding more in, right? So there is an analysis for that as well. The mathematics are much more involved. So that's why I didn't go into it here, but yes, there is the analysis saying that, you know, this finding the hyperplane that has maximal margin is more stable even on new data sets that you don't, data points that you don't see in your training set. Right, so any other questions on this? Okay, so as many of you pointed out, this is for the linearly separable case, right? Most of the time, the data is not linearly separable. And so what do we do when the data is not linearly separable? Right. So here, I just created more data points, this guy, and this guy. So now, okay, before we get to that, so there's sort of 2 forms of badness going on here, right? In this case, we're still classifying this guy correctly, but we're getting dangerously close to misclassifying this guy. Well, this guy, we misclassified this guy. Right? So you might think that there are sort of 2 forms of sort of potential errors that we can, or potential sort of mistakes that this optimization formulation might make. We're actually going to lump both of those into the same mistake. And so this is called the soft margin support variation. We're still going to want to find the margin, right? Our goal is to still find this margin. But we're going to tolerate some amount of margin violations. So we're going to allow some subset of the data points to quote-unquote violate the margin. And we'll do that by introducing what's called a slack variable in the optimization problem. Right? So let's walk through this. This optimization formulation. So without this part and without this part, it's the same as before, right? And so, excuse me, C here is a tuning parameter. It's a hyperparameter of the model. So you set it as you please. If you set C to be very large, this minimization problem cares more about this term than this term. If you set C to be very small, let's say 0, then you don't care about this term at all. You only care about this term, right? And these slack variables are now negative. So, so for this data point, right? For this data point, y times its label, which is -1, times its score, is going to be a negative number, right? It's a negative number, which means that for this constraint to be satisfied, for this negative number to be greater than 1 minus the slack variable has to be some large positive number. And in fact, the slack variable is exactly the distance from this margin to the point, right? So the slack variable in code is exactly this distance, and for this data point, the slack variable encodes this margin, this amount of margin violation. So for this data point, this number is still positive, right? This number is still positive, but it's less than 1. It's still positive because it's still classified correctly, but it's less than 1. And so in order for this to be bigger than 1, you have to choose a slack variable that subtracts from 1. In this case, the slack variable is less than 1, but it's still non-zero. And the goal then is to minimize a trade-off between maximizing the margin, right? Is to optimize a trade-off between maximizing the margin, as noted here, versus minimizing the slack. So if we set C to be very high, right, then we are very intolerant of margin violations, and we want the margin to be as small as possible. We want the margin violations to be as small as possible, in which case we might draw the line, let's say right here. We might draw the hyperplane right here, and then the margin would be something really small, and then we would just tolerate only a very small amount of margin violations, right? We'd only have to suffer small if we set C very large. If we set C very small, then we almost don't care about margin violations at all. Right? And so this is the full formulation of the support vector machine in the non-separable case. Right? Size of margin versus size of margin violations. Yes?
Question. So in this case, with the soft margin constraint, can we still ensure that that constraint, there's like a quality condition? Like what do we find support vector in this case?
Yes. So in this case, these are support vectors.
Okay.
Yeah. Anything that sits on or violates the margin is a support vector. Yeah. In optimization terminology, for any data point where this inequality is an equality, is a support vector. Right? Because as before, if it's an inequality, then it's irrelevant. You could take that data point out of the training set, it won't actually change the solution. Right? It's only if it's an equality. Right? And furthermore, for this data point, right, you actually want the slack variable to be as small as possible because you're trying to minimize it. Right? You're trying to pay as little of a slack penalty as possible. Right? And so you want the slack penalty, you want this variable to be exactly the distance of the margin violation and no bigger. Right? Because you're trying to minimize it. Therefore, it will be an equality here. Right? Yes?
How do you decide the value of the slack variables?
How you decide? It's part of the minimization problem.
Oh, okay.
Yeah, so the learning objective says, and I'll talk about what loss function this is optimizing. So this is actually optimizing what's known as hinge loss, which I'll talk about in the next slide. But yeah, it's a free variable in the optimization. So when you actually solve this thing, you're going to solve this using stochastic descent. There's one form that actually solves for there's a few different ways to solve this problem, but one version of solving this problem was solving the side variable as well. Although typically you can just set. Yes,
So for C is greater than some value, we should not have
you should have any what?
some data sets. That, let's assume just there's a like the black one, the black dot. It just moves a little to the left. So there's no specific line separating. You're assuming that there is a line that you can draw.
No, there is no.
I mean, if you
I believe I created this example such that there does not exist any line that can separate the black and white. Okay, so I may have created this example a little bit carelessly. There may be a line right here, but let's assume that there is no line that can separate the black and white. There's no line. So there's always a solution to this problem, right? So, this is a quadratic, and this is linear, right? So, like, even if you set C really, really large, at some point you still need W to do something, like for this minimization problem. Yes.
C is non-convergent if it's negative, right?
C has to be non-negative. Yeah. C is a non-negative hyperparameter of the problem. Yes.
So, in the case of the slot variable, will there be a case where psi is 0 and quality is held always? So for this example, we still have 3 points on the dotted lines, I guess. I don't know what to call them.
Right.
But will there be a point, will there always be points for both sets on the dotted lines?
Oh, in the case of non-linearly separable?
Yeah.
It's a good question. I think I cannot be 100% certain, but I think the answer is no. In the non-linearly separable case, there does not need to be points that lie exactly on the margin. I think the answer is no. That's you do need at least one positive, one negative point whose constraints are tight, with that achieves equality on here. But I don't believe you need points that lie exactly on the margin. I don't believe so, but I'm not 100% sure. Yes?
So, just to clarify, so if C is 0, then you can allow the slack variable to be as arbitrarily large, right?
Yeah, no one actually sets C to 0 in practice. Let's say C is a non-negative number, or excuse me, positive number. Yeah, setting C to be 0 would create some degenerate cases.
Then by C being small, it means that you allow more things to violate.
Right, if you set C to small, you care more about having a large margin and less about margin violations. Yes?
So if the problem is perfectly linear separable, the result will always be the same regardless of the value of C, right?
No. Let's suppose these 2 points didn't exist. And the problem was, so the problem is linearly separable.
Yeah.
I can set C to be really, really small, right? And I can have a margin that's this big, and I'm going to have some margin violations, right? But there exists a small enough C for which that might make sense. Yes.
Do people typically pick C themselves, or is it just some kind of hyperparameter optimization thing?
You pick it by using a validation set.
Okay, sure.
Yeah. You'll become very familiar with that during the Kaggle competition. Okay, so now I'm going to talk about the loss function that's actually being optimized. Oh, sorry, one more question.
You pick the square points at the beginning and then you count those 2 lines.
Do I pick the what? I'm sorry?
The square points, like those points on the border.
Oh, no. They're picked automatically by the optimization problem. Yeah. Okay, so now I'm going to talk about what is the loss function that we're actually optimizing here. Okay? Because what I wrote here doesn't necessarily, at least not sort of in a super obvious way, leads you to understand what is the loss function being optimized here. Right? And so what's being optimized in the SVM is what's called the hinge loss. Right? And so I can write out the loss, right, of a label, let's say +1 or -1, and the score, the linear score, although it doesn't need to be linear, but let's say we have a linear scoring function of this example, then this loss, the hinge loss, says it's the maximum between 0 and 1 minus the sign of the true label times the score. Right? So if the score is the same sign as the label, then this number is positive. If the score is the opposite sign as the label, this quantity is negative, right? And in particular, if the score, let's say the label is +1, right? Let's say the label is positive. If the score is greater than or equal to +1, then the right-hand side of this max operator is going to be less than or equal to 0, which means this thing is going to be 0. The loss is going to be 0. If for y being +1, if the score is less than +1, let's say it's 0.5, then 1 minus 0.5 is 0.5, and the max over 0 and 0.5 is 0.5. So if your score is 0.5, then the loss is 0.5. And in fact, this score increases linearly as the loss increases linearly as the score of the function disagrees with the label at a linear rate. And as long as the score of the function is above +1 for positive y, then the loss is always going to be 0. So the loss is 0 until it's less than +1, and then it starts increasing linearly. And that is the hinge loss, and you can check mathematically that this loss function is exactly equal to the quantity captured by the slack variable. Right? So I can replace these slack variables and these constraints as well by just this loss function. One thing that we'll talk about more in the next lecture from this perspective, right, is that this term can be viewed as a form of regularization, which is trying to keep the model as simple as possible. And we'll talk more about this in the next lecture. So, now hinge loss can be viewed as another surrogate to 0-1 loss. An alternative to surrogate 0-1 loss as opposed to squared loss, right? So if we want to minimize hinge loss rather than squared loss, it has a number of desirable properties, right? First of all, one thing that's kind of weird about squared loss is that if our model predicts a really high score, right, like a score of 2, squared loss is, oh no, that's for an instance with label +1, squared loss is, oh no, that's wrong. That's wrong. And that seems kind of weird, right? Whereas hinge loss says, that's fine, right? And hinge loss says, well, while the model, if your model is at risk of classifying this data point incorrectly, we'll start increasing the loss, right? If your model gets it way off, Well, the loss will increase linearly rather than quadratically. So if you have random outliers in the data, right? So some data point, if some data point sign got flipped randomly, right? For whatever reason, and so it's an outlier in your data set, then the amount of penalty you pay for that data point is only going to scale linearly with how badly your model misclassifies it. Whereas for square loss, your model is going to pay way more attention to. Right? So for square loss is much more sensitive to outliers in your training set than hinge loss is. Any questions on that? Yes?
Can we define a square hinge loss?
Yes, in fact, it exists. A squared hinge loss exists. Was there a purpose to the question? Like, if you feel it's going to be better?
Like, what if it's saying on the right side we don't want square loss increase, then we make 0 and 1.
You can, in fact, define a squared hinge loss. People have done that. I'm not sure what the benefit is. You can, yes. Okay, so I just want to remind you guys of the perceptron learning algorithm, which says make an update if you make a misclassification in the direction of the data point times the label, otherwise keep the model the same. And then we talked about how this was the loss function that the perceptron is implicitly optimizing. So the SVM or hinge loss is actually has a very close connection to the implicit loss function that the perceptron is optimizing. The main difference is that for the SVM, the loss starts increasing as you're within, if you're not classifying the examples correctly to within by some margin, right? So in fact, the SVM loss will give you a more stable model than the perceptron. Okay, so just to summarize for the support vector machine, I gave you two interpretations of it. Right? One based on geometric interpretations, margin versus margin violations, right? One based on loss minimization, right? So model complexity as measured by the square norm of W. Again, we'll talk about this in depth next lecture. Versus the hinge loss, the mispredictions you make on data set, right? And from these two interpretations, we arrive at the equivalent learning objective, right? And so these two interpretations are just two different ways of viewing the exact same problem. And this will often be the case as you think about, when we look at different types of machine learning problems, is that they are often have multiple ways of interpreting what's going on, and typically all those different ways are valid, right? And you could derive the learning objective or the learning algorithm using any of these perspectives, right? You'll find that to often be the case in many machine learning problems or machine learning algorithms. Any questions on that? Yes?
So can you go back to one slide? Comparison to perceptron, the x label was like y times f of x, but the slide before this one, with the
Oh, I mean, right. So, right. I should have been more consistent. The thing is, if y is +1, this doesn't matter. You'll be right. I should be more consistent. So a comment on optimization. So the hinge loss is not smooth, right? So, it has better behavior than 0-1 loss, obviously, right? So what it's saying is, if I'm over here, I have a slope that tells me which direction to go to get better. If I'm over here, I don't care, right? That's what hinge loss is saying, right? But, you know, it does have a point of this kind, of non-differentiability right here, right? So it's not differentiable, it's not. And so how do we optimize for it? So one popular way of optimizing things like hinge loss is what's called subgradient descent, which is a generalization of gradient descent. And we'll discuss subgradients in more detail in the next lecture. Because in fact, this function is differentiable everywhere except for this part here, right? Which is also known as the hinge. Okay, so now we'll move on to logistic regression. So this is sort of the formula for that people use when motivating logistic regression. So suppose we want to model the conditional probability of y given x. So given this x, what's the probability that y is plus 1 versus minus 1? And so this is the formula. Right? So we still have this linear scoring function, but it's in an exponent. You put it into an exponent, and then we normalize by if the label is plus 1, or by its label, or its opposite label. That's why this negative is here. And so what you see here is the probability of y times of y given x, where if y times f of x is a large positive number, then the probability goes to almost 1. If y times f of x is a large negative number, the probability goes to almost 1. We can also write it in this form. If we simply divide the numerator and the denominator by this quantity, we get this formula, which is much more familiar to most people in the machine learning community. This is the standard formula people use in logistic regression. Although I think this one, in some ways, makes more intuitive sense. And this is known as a log linear model. Because if you take, because it's linear inside the exponent, is sort of the reason why. And this allows us to, as we'll talk about more as we move on to probabilistic models, this allows us to model not just a classification, but the probability of it being this class versus another class. So how do we train such a model, right? We still have a linear scoring function, but it's in this form, right? How do we train such a model? So we have our training set, right, of x, y pairs, where x is some real value vector and y is a binary label, plus 1 or minus 1. Sometimes in logistic regression, the label is 1 or 0, in which case you have to shift things around in terms of the algebra, but those are just minor details. And then we want to what's called maximize the likelihood, which is find a W and B that maximizes the ground truth y, the probability of the ground truth y given the x, right? So one question is, well, why does this decompose into a product, right? So we want to, why does this decompose into a product of each individual xy pair? Does anyone have any guesses to that?
Because the sum of all exponential.
I'm sorry?
Because the sum of the exponential.
Right, but that's for an individual training example, right? This is for different training examples.
You want the graph to be more
Not sure what you mean by that.
I mean the grading of the graph.
So this has nothing to do with how you optimize. It's about the statistics of the learning problem. Yep.
Yeah, if you assume that the training examples are independent, then you're getting the joint probability of those given your...
Correct. That's right. So if we assume that each data point is sampled from the training set is sampled independently from the test distribution, then the way we model every probability independently of each other, which means that when we maximize the joint probability, we maximize the product of the individual ones. if you're, we'll talk more about things like independence and how probabilities decompose multiplicatively if you make independence assumptions in the probability recitation in a week or two. Okay, so why might one use logistic regression? So SVMs, in many cases, are better at classification, assuming that a margin exists, or a margin exists with very few sort of margin violations, right? But an SVM, if you actually want to get a probability, right? What is the probability that this data point is it has a label of +1? Is it 70%, right? Then, can we sort of calibrate the SVM score such that we get this, we can interpret the probability out, right? And so here, we see that, as the score, in this case, I took this example from a different model class, whose the symmetries of SVMs look the same. As the model score increases, the probability increases in a nonlinear way. Right? So you cannot directly interpret the raw scores of the SVMs as probabilities. Right? So they're not well calibrated. Logistic regression, turns out, much better calibrated because they're indeed trying to model the conditional probabilities directly. So now I want to talk about a loss function for logistic regression. So this was the original formula that I gave you, right? So the score, the exponentiated score of the exponentiated sign score, so you have the linear score of the model class times the label plus or minus 1. You divide by that number plus the exponentiated score for the opposite class, for negative here. We could just generically refer to this part as the function, as the model score, right? And so that's this number quantity here, and we want to for training, we want to find a WB that maximizes the conditional probabilities of the ground truth y's given the x's from the training data. So we want to actually turn this into a loss function that we can minimize. So I did a couple of manipulations in this step. The first thing I did was take the negative log of this whole thing, right? Which turned a maximization problem into a minimization problem. And then the log of the product is equal to the sum of the logs, right? So I push the log inside the product and then turn the product into a sum, right? And so now I have a minimization problem over the sum of the negative log probabilities of the training data. And this will be our loss function for training. And this is known as log loss. And you can check that the solutions of these two problems are the same. Right? They have the same solutions because I just did a bunch of I did a negation, turned a maximization problem into a minimization problem, then I did a monotonic transform. Right? Yeah.
Is there a way to show that one of those, that the product of the sum is always more cost effective than the other?
What do you mean by cost effective?
I mean, if those two statements are identical, then the only, why take the log? Is it?
Because if you want to do stochastic gradient descent, right? You want the loss function to be additively decomposable. Actually, that's the entire reason.
What?
That's the entire. That's basically the entire reason.
Okay.
Yeah. Yes.
What's the increase in computational loss? Computational cost when you do the loss of it, versus if you're just working with the original linear formulation?
Well, so what's the actual computational cost if you take the log?
The increase, yeah.
So it's not that much. It's not that much, especially if you actually manipulate this quantity here. I'll describe what that means. So I'll describe what that means. So you can actually simplify this formula a lot if you manipulate it. But I'll get to that in a few slides. So it's now applying hinge loss versus log loss versus 0-1 loss. Right? And so this quantity here is actually asymptotically linear. linear as the function. So again, it's, the target label is +1. So the ground truth is +1. So as the function sort increasingly disagrees with the target label, this function is asymptotically linear over here. So it looks like the hinge loss in the asymptotics of this regime. And then it's asymptotically 0 in this regime, right? So it's in this middle regime that it has a different behavior than hinge loss, right? Where the curvature is superlinear. But otherwise, it's actually, in the in extremal cases, the behavior is actually quite similar. So hinge loss basically says, as long as the model score is beyond some threshold, I don't care at all. And if the model score is not beyond that threshold, I care at a linear rate. And log law says I start caring before that, basically. And I gradually converge to a linear rate. And I'm sure this is a very inquisitive and curious group. I'm sure someone might ask, is there some combination of hinge loss and log loss? And in fact, yes, there is. There's an entire family of loss functions that sit in between, of which hinge loss and log loss are two instances of. So you can actually take this curve and make it sharper and sharper and sharper until it's exactly hinge loss, right? Although I won't go into details of that. If someone's interested, ping me, I'll give you a link to the paper. Okay, so I'm going to show you a quick derivation of the gradient for one data point to answer some of the questions about computational costs of computing the gradients. So we take the gradient with W from a single data point with a negative log probability. If you recall that this is the formula, right? What that means is, you take the log, you take the log of the numerator minus the log of the denominator. The log of the numerator is this thing, and the log of the denominator is this thing. This is a linear function, so we do that, and we do this. So I just simplified this part. You apply some chain rule on the gradient of the log, you get something like this. Again, here we just apply the gradient operator to these two things, and rearrange the terms, because if the gradient of this guy, this thing falls out by chain rule, and so we can collect all these terms on the outside of these parentheses. And we can actually realize that these terms can be manipulated to look like this, right? So the gradient is actually, the feature vector times the label times 1 minus the probability of classifying it correctly given the current model. This is the prediction of the current model, right? So if our current model is super confident that the prediction is the correct label, then this term, this added multiplicative term, is basically 0, in which case this contributes very little to the total gradient of the loss function, right? If our current model is super confident on the opposite label, right, then this term is almost 1, right? Because in which case, because this probability will be almost 0. In which case, this particular data point will contribute a lot to the gradient of the overall loss function over the training set. But note that it will contribute. This coefficient here is bounded by 1, right? So that it's going to scale linearly in the outlier case. Okay, so I gave you two interpretations. One from maximizing likelihood of the training set under a conditional probability model. One is as minimizing log loss. Right? We define a new loss function, and it has some geometric properties. We compared it to hinge loss, and then we're just going to say we're going to minimize it. Again, they are equivalent. They lead to the exact same optimization problem. So if you take either perspective and you start deriving the learning objective, you end up with the exact same learning objective. Right? Both perspectives are valid. Any questions on that? Okay, I'm going to just go very quickly over neural nets. We're going to spend two full lectures on this later in the course. We'll look at fairly shallow networks here. So just some terminology. This is borrowed from computational neuroscience. So a neuron, right, is the following operator. It takes in a feature vector x here. Its x is three-dimensional. It does a weighted sum of x. It applies some nonlinear transform to it, and then it spits out a y, right? So one example. So this is going to be this part is basically like the linear score, right? And then we apply, let's say, a sigmoid function to it and get the y. Right? Looks like this. So can anyone tell me what this looks like? Correct. Trivial neural net is exactly logistic regression. That is correct. Here's a two-layer neuron, right? So we have two layers of neurons, right? So each individual neuron you can think of as logistic regression. Although if you use a different transfer function, it will no longer be logistic regression. But let's say you can think of each individual neuron as logistic regression. And then this neuron is going to take the outputs of the previous neurons and sum them up and do a nonlinear transform on them and spit out. And this is known as a hidden layer. This is a nonlinear function now, right? Because it's a linear combination over a nonlinear transform over a linear combination of the raw inputs. This is now a nonlinear function. This is the first nonlinear function that you've seen in the class so far. And in fact, one can show, although it's not a very useful theorem, that you can approximate arbitrary functions with a two-layer neural net, as long as the hidden layer is large enough. Right? So, as we'll talk about more later in the course, deep neural nets are simply artificial neural nets that have many, many, many hidden layers. Right? Some of the ones used in production these days have over 100 hidden layers. Right? So why would I prefer a deep neural net over a very fat, quote-unquote fat, shallow net? One is that it's compact, right? You can, people have been at least working, at least in, if you think about the analogy of the circuits, right? If you think about EE classes, right? A neural net, in some sense, is very similar. This is very similar to a circuit design, right? Where the depth of the circuit gives you a lot more expressivity than a shallow circuit with a lot of gates, right? It turns out that deep neural nets can often be easier to train than shallow neural nets because the depth actually in itself imposes a form of regularization. We'll touch on that later in the course. So this is discussed further in the deep learning lectures. I just want to sort of briefly introduce this. Training neural nets is pretty straightforward. You just train using gradient descent or stochastic gradient descent, right? You could write out the models. You could recursively call the other neurons in the lower layers, and then you don't need to follow this right now in the lecture. I just wrote out the gradient for W2, which is this guy. And so for any loss function, right? W2 is this guy, sorry. And W1M is one of these two. So it's just a bunch of chains, basically. This is also known as back propagation in the community, also known as chaining. Okay. So far, we talked about different loss functions can be derived from different interpretations. We briefly touched on different anomaly model classes, neural nets, which you can compose with any of the loss functions we talked about in class. It's simply a nonlinear function class. Typically, there's no closed form formula for training. Some of you have noted that for squared loss and linear models, you can just solve it. There's an analytical formula that solves this optimization problem. For all of these, there's no analytical formula. You have to use gradient descent. Okay, so for the final, I guess, 10 minutes or so, I'm going to talk about different forms of evaluation metrics. So, you can evaluate for classification. You can say 0-1 loss, or you get it right or you get it wrong. For regression, you can say squared loss. How far am I from the correct prediction? There are, of course, other ways to do an evaluation as well. So here's an example, right? Suppose the two labels are has cancer or doesn't have cancer, right? So a model predicts if the patient has cancer and a model predicts has cancer, in some sense the loss is going to be low, probably 0, right? If the patient doesn't have cancer and the model predicts has cancer, let's say the loss is medium, right? If the patient has cancer and we predict don't have cancer, that is a horrible misprediction, right? And then if the patient doesn't have cancer and model predicts doesn't have cancer, loss is again low, probably 0, right? And so for 0-1 loss, right, we view the off diagonals as having equal penalty, right? It would be 0, 1, 1, 0 would be the cost matrix of 0-1 of classic 0-1 loss. And here it's something else, right? So 0-1 loss is a special case of a more generic notion of a cost matrix, right? So how do we optimize for a general cost matrix? There is no universally accepted way, right? Here's one of the simplest approaches, which is simply cost balancing, right? So if this is my cost matrix, right, then I'm just going to simply, in my minimization, in my learning objective, I'm just going to simply weight this type of misprediction, right, 1,000 times more than the other one. So this is probably the simplest way of doing cost-sensitive learning. There are other ways as well. Other concepts that are interesting, important, include things like precision and recall, right? So here, let's talk about first. Let's talk about things like true positives, false positives, stuff like that. So so a positive here refers to has cancer. So positive. So here we're always here we're thinking about the regimes where the positive class is rare, right? So the majority of the people we encounter, or the inputs that we encounter, are of the negative class, right? So a true positive is where the ground truth is positive and our model predicts positive. A false positive is if the ground truth is negative and our model predicts positive. A false negative is when the ground truth is positive, our model predicts negative. And a true negative is when the model predicts negative and the ground truth is also negative. So precision is true positive divided by true positive plus false positive. So this number divided by this number plus this number. So this cell divided by the sum of this row. So of all the positives that our model predicts, what fraction are actually positive? Recall is true positive divided by true positive plus false negative. So of all the positives in the test set or the validation set or whatever it is that we're sort of evaluating this over, what fraction did we actually predict as positive? And so we can actually compute like a precision recall curve, right? So one way to compute these curves is I'm going to vary my B, right? I'm going to train a model. I'm going to vary my B, my threshold for predicting positive or negative, and I get these curves, right? If I predict everything is positive, if I predict everything is positive, I get close to 0 precision, right? But I get 100% recall, right? So everyone has cancer. I'm never going to miss anyone who doesn't have cancer. Right? It's not a very useful model, right? So typically we want to be on this corner, right? We want models that have curves, precision recall curves, that hit this upper right corner as closely as possible. So here's an example about another, we're going to talk about rankings now. And here's an example for a search query, right? Where most examples are negative or not relevant, and a few examples are positive, right? So one ranking measure is, well, okay, if we issue a query and the user only looks at the top 4 results, then what that means is if we score, if we rank all the examples by our model score, right? Because we can, so we take the 4 most positive or highest scoring examples by our model, and we rank them, and we show those to the user, right? And half of them, right, were positive, and half of them negative. Then that's precision that's called precision at 4, and in this case we get a precision at 4 of 50%. So this is a rank-based notion of precision, right? We're going to rank all the examples by the model score, and we're going to look at the top K, and we're going to say those are all the ones that we're going to label as positive. The rest will label as negative. We could also do recalls at 4. If we take the top 4 as the positive examples that we're going to predict positive on, what fraction of the actual positives do we get in those top 4? And so here, the recall of 4 is 2/3, because there are 3 positive examples. Okay. So here, these type of evaluation metrics says, if I'm using machine learning for some downstream application, I only have time to look at the top scoring examples that the machine learning model predicts on. So whatever the machine model predicts on that scores highly, that's what I care about. And these are evaluation metrics that look at that. We can also do pairwise preferences. So if we take a look at every pair of positive and negative examples, and again, the positive examples are the rare class, then there are 2 pairwise disagreements. These 2 pairs of examples were ranked incorrectly, and these 4, so these 2, these 2, these 2, these 2, are ranked correctly. So these are pairwise ranking preferences. And if you look at pairwise ranking preferences, then there's a concept known as the ROC area, or receiver operating curve. Right, so here's an example. We have a ranking of 5 examples. Green is positive, red is negative. So there are 6 possible pairs of positive and negative examples. These 2, these 2, these 2, these 2, these 2, these 2, these 2. Sorry. These 2, these 2, these 2, these 2, these 2, these 2, these 2. And so of all the possible pairs of positive and negative examples, half of them are ranked correctly. Positive is ranked above the negative. Half of them was ranked incorrectly. And in general, we want, if we rank everything perfectly, the ROC area, our area in the ROC curve would be 100%. And the last ranking measure we'll talk about is average precision. I'm running a little bit behind time, so I'm gonna skip this one. It's not on the home line. So I'm gonna skip this one in the interest of time. I want to close by a discussion about other challenges as well. So here's an application of computer vision where you want to label, you want to identify all the vehicles in this image, and you want to draw bounding blocks around that vehicle, right? And so there's a number of design decisions that goes into this type of task in terms of evaluation, right? So first of all, this is the actual bounding blocks in red. Our model predicted this bounding blocks, right? And so, at some point, the overlap here is good, and therefore we say this is a correct prediction. If the overlap is not good, it's an incorrect prediction. How do you decide when the overlap is quote unquote good enough, right? And here we have a duplicate detection, right? So here the model predicted 2 different bounding boxes for the same detection, for the same car. So only one of them gets to be labeled as correct. The other one must be labeled as wrong. Maybe, right? Maybe not. It depends on the application. Furthermore, what is the learning objective, right? This is a complicated evaluation metric. Does it make sense to write out a learning objective that maximizes this optimization objective? We have similar challenges in videos, right? For example, if there's an activity like running, like over a sequence of frames, right? And we want to put a temporal bounding box around the running activity, then, did we capture the full running activity? Did we cut off our prediction of when the person is running before the person actually stopped running? What if we predicted the person was running on two separate instances when it was a single instance of running, right? Just like in this car case, we predicted that there were two cars, right? If we're using this for census, right, we would have in this case overcounted the number of cars, and in this case undercounted the number of cars, right? If we're using this as a census tool, right? And there are other examples too, like heart rate monitoring. Can you detect things like arrhythmia? Where is the arrhythmia happening? Can you put a temporal bounding box around the arrhythmia event in a way that's useful? I could say the entire 1 hour there's an instance of arrhythmia in here somewhere. That's not very useful. So these are all questions that you'll have to grapple with as you deal with these issues on a practical level. So that's it. So we talked about different evaluation metrics and different scenarios. A lot of these evaluation metrics are focused on the case where the positive examples are rare, right? And there are other challenges too, like localization, like drawing bounding boxes in some sort of continuous domain. And so next lecture we'll talk about regularization and lasso. And remember, tonight is the recitation on linear algebra. Thanks.